Hey guys, welcome back to the last video got cut off, so we're gonna continue back from where we left off. So question C, Jay stops swinging her legs when the swing is at its maximum displacement. On the grid below, sketch a graph of her displacement over the next 3 periods. Include the values for time and for the initial displacement at t equals to 0. So Jay stops swinging her legs, that's going to be our t equals to 0, and that's when the swing is at the maximum displacement. So the maximum displacement would be this point B at the top of the circle here, so this point B, and that point B is going to be equal to the amplitude, which is 0.31 meters. So the maximum displacement would be is equal to 0.31 meters. So t equals to 0, our displacement, so our amplitude equals 0.31 meters. So we'll just say that we'll say each vertical box is 0.05 meters. So 1, 2, 3, 4, 5, 6. We can say this is 0.31 meters when t equals to 0. So this on the horizontal axis. On the horizontal axis is time, and on the vertical axis is displacement. And we want to sketch out the next 3 periods. So in this question, when she stops swinging her legs, that means she cannot replace the energy that is lost to heat and sound, which means that over time the system is going to lose energy due to heat and sound, which means that the amplitude is going to get smaller and smaller over time. However, it's important to note that the time period of each, so basically the period of oscillation is not going to change. It's just that the amplitude is going to decrease over time. Okay, so the time period doesn't change. So the next 3 time periods, and how long was each period? The period was 2.4 seconds. So we can say that for each 1, 2, 3, 4, 5, 6, 7. Okay, for each 8 squares, we can say that's 1 time period. So 1, 2, 3, 4, 5, 6, 7, 8. So this is 1 time period, 2 time periods, 1, 2, 3, 4, 5, 6, 7, 8. So that'll be our third. Alright, so our graph is going to start at a maximum displacement of 0.31 meters. So now it's good to look back at your reference circle. So as you can see, we're starting at point B. After 1/4 of a time period, we're going to be back at the equilibrium, and the equilibrium means that the displacement will be 0. So after 1/4 of the time period, 8 squares is 1 time period, so after a quarter of the time period, which is 2 squares, we're going to have a displacement of 0. So right here, we're just going to pass through this point. After another quarter, so right now we're at point, we'll call this point Z. Call this point Z. So after another quarter circle, we're going to reach the maximum displacement, but in the opposite direction, okay? So we're going to reach our maximum displacement, but opposite direction. However, at this point, it's going to start losing energy to heat and sound. So this displacement is going to be less than the 0.31 meters that we started with. So after another quarter cycle, so another 2 squares, we're going to have less displacement. It doesn't matter how much less displacement, unless it's all that is important is that you show that the displacement is decreasing over time. So after another 2 time periods, we're gonna have less displacement. We'll just say here, 1, 2, 3, 4, 5, say somewhere here. And then, as you can see, if we go back to our reference circle, after another quarter cycle, we're going to reach back to point Y. We'll call this point Y. We're going to reach back to point Y, which is at the equilibrium again, which means that the displacement is 0 again. So after another quarter cycle, we're going to reach displacement equals 0. So another 2 squares are going to reach displacement is 0. And then the cycle cycles back to the maximum displacement, except the difference is this time that the maximum displacement will be less than the 0.31 meters we had initially, and that's because that some energy was lost to heat and sound. So this, after 1 time period, we're going to have a smaller displacement, a smaller maximum displacement, so somewhere here. And then it continues. So after another quarter time period, we're going to reach the equilibrium again. So displacement is 0. And Once again, we're going to reach, and after another quarter cycle, we'll reach the negative maximum displacement, which is going to be less than the previous maximum displacement because, once again, due to energy loss. So, say somewhere here. And after another quarter cycle, we're going to reach the equilibrium again. So, displacement is 0. And after the second time period, we're going to have further decreased displacement. And the cycle continues. So we'll say after quarter will be at equilibrium. After another quarter, we'll be at the negative maximum displacement. Then we're going to be, after another 2 squares, we're going to be back at the equilibrium. And then finally, we're going to reach our final time period with a very small displacement. So now all that's left is to join up the dots. So you can just say draw. Okay, it's really hard to draw on this device, but I'll try my best. Oh, that's pretty bad. Oh, that's pretty bad. Right, so your graph should look something like this. So as you can see, each time period remains the exact same for each oscillation. However, the maximum displacement keeps decreasing for each time it cycles around. So for this graph, you should be able to get up to a merit grade, and that's assuming that you have correct time period. So time period stays constant, and you have the decreasing displacement over time. Decreasing displacement over time. And that will get you a merit grade. To get an achieved grade, you only need to have one of these. So either the time period is correct or the displacement is correct. You'll get an achieved. Question D. J moves to a new swing that is a tire hanging vertically on a single chain. The system is a conical pendulum. J travels at 2.61 meters per second around a circle of radius 0.411 meters. The total mass of J and the swing is 70 kilograms. Assuming friction and mass of the supporting chain are negligible. Calculate the tension in the chain supporting the swing and the angle of the change of the vertical. So we're trying to find the angle theta, and we're trying to find the tension force. We'll call this tension force tension T, and angle theta. So the first thing we should do here is we should label all the forces acting on the ball. It's not a ball, it's a tire. So we should label all the forces on the tire. So on the tire, we're going to have a force of gravity, which is acting downwards, as well as a tension force from the string, which pulls it around in a horizontal circle. So when the tire and J moves around in a horizontal circle, the vertical height isn't changing, and that means that the force of gravity is equally balanced out by the Vy component of the tension. Okay. So if we draw this up into tension, we'll say there is a Vx tension and a Vy tension. We'll say this is not Vy. We'll say Ty and Tx. The Ty and Tx. So as you can see, in this case, we have the horizontal circle. That means the vertical height is not changing, and that means that the force of gravity is equally balanced out by the Ty component. So the Ty component is equal to the force of gravity component. Now Tx is acting towards the center of the circle, and that is also going to be our centripetal force. So Tx is going to be our centripetal force acting towards the center of the circle. And after we figure out both of these components, we can use this in order to find the total tension force and use Pythagoras to find out tension force and the angle. So we know that the Fg, so basically in our statements we can say that tire moves in a horizontal circle, meaning vertical forces are balanced. So hence you can say that Fg is equal to the Ty component. You can say that the Tx component x towards center of circle, it is the centripetal force. Hence, you can say that the centripetal force is equal to the Tx component. So now we can figure out our Ty and our Tx. So our tire is 70 kilograms, so our Fg is equal to 70 times 9.81. 70. That gives a vertical weight force of 686.7 newtons, and this is equal to Ty component as vertical forces are balanced. We have our Tx acting towards the center of the circle, so Tx equal to Fc, which equals to mv squared over r. We have our mass is 70, we have our speed, and we have our radius, which means we can find out our centripetal force. So Fc is equal to our mass is 70 times speed is 2.61 squared divided by the radius, which is 0.411. So 2.61 squared times 70 divided by 0.411. That gives an Fc of 1160.21 newtons, and that is equal to our Tx component. So right now we can draw a rough vector diagram. So we have our Tx, we have our Tx, we have our Ty, and we have our T tension force. We have our Tx, which is 1160.21 newtons, and we have our Ty, which was 686.7 newtons. So now we can use Pythagoras to find out our tension force. So a squared plus b squared equals to c squared. In this case, our c is our t, as is the hypotenuse. Ty and Tx will be our a and our b value. So 886.7 squared plus 1160.21 squared equals to t squared. So 386.7. So we should get that our tension force is 1,348.2 newtons, 0.20 newtons. And now we need to find out this angle theta. So in this case, we can use the inverse tan. So we have our opposite side, which is Tx, opposite side. This is adjacent and hypotenuse. So we can use SOHCAHTOA, we can use tan of Tx of Ty. So tan theta equals to Tx over Ty. So therefore, inverse tan of 1160.21 over 686.7, and we can use degrees for this one. So inverse tan of 1160.21 divided by 686.7, and that gives an angle of 59.38 degrees. Alright, and that's all the question asked for, I believe. So calculate the tension, change the point of swing, and angle. Okay, so that would be your final answer. So you have your angle and your force. Both of these will get you an excellence grade. To get a merit grade, you only need one. So either the angle or the tension force, you'll get a merit grade. To get an achieved grade, I think if you work up to this step here, so figuring out your Tx and your Ty components will get you an achieved. Alright, so thank you for watching this video for the 2019 Level 3 Mechanics video. I hope you understood everything. I'm sorry if some of the explanations were a bit hard to understand, but hope you enjoyed, and I hope